Fontana Dam, the highest east of the Rocky Mountains, was built by the Tennessee Valley Authority across the Little Tennessee River in the Great Smoky Mountains of western North Carolina. Fontana fulfills three purposes in the integrated system of dams which control the waters of the Tennessee River and its tributaries. The reservoir has a controlled flood capacity of over 700,000 acre-feet, which holds back water during the rainy months and releases it during low flows through two 67,500 kilowatt generating units, thus producing electric energy, and at the same time helping to maintain stream flow in the main river as an aid to navigation. Into the construction of a modern dam go materials and equipment from all sections of the country. Cement from Tennessee, belt conveyors from Ohio, penstocks from Alabama, turbines and control gates from Wisconsin, transformers from Missouri, generators from Pennsylvania, circuit breakers from Massachusetts. The technology of American industry was focused and applied with engineering skill at this remote wilderness site. A bridge and 10 miles of access road were built through rugged terrain to connect the site with main highway facilities. Access by rail was obtained by extending the tracks of the Southern Railroad 2 miles downstream to the dam site. Production of aggregates for concrete requirements was a major operation. The rock was a tough, dense, massive quartzite formation, interbedded at some points with thin layers of slate or phyllite. Workmen were recruited from all over the country to build Fontana. Employee housing was a major problem. A construction camp near the site provided living quarters in dormitories and tents for 3,000 workmen. A village which provided 900 housing units for employees and their families was located 2 miles away and had all the facilities of a modern town. The first work on the site was the stripping of the overburden from the foundation in preparation for placing concrete. The depth of the overburden averaged from 10 to 20 feet in the riverbed, but ranged up to 90 feet on the abutments. The final scaling was done with pneumatic tools. Some of the rock in the foundation of the left abutment dipped downstream as much as 30 degrees. Horizontal steps were cut in the surfaces of these beds by close drilling and broaching where the slope exceeded 1:10. The more than 6 million tons of rock required for concrete aggregate were taken from the quarry located about 1 mile below the dam site. 7 well drill rigs drilled primary blast holes 9 inches in diameter, 30 feet apart, and about 30 feet back from the face of the quarry. The face was over 500 feet in height and was developed in 2 steps. Loading the holes with 100 tons of nitrogen took over a day. Up to 600,000 tons of rock were brought down in a single blast, representing about 3 tons per pound of powder. The larger rock from the primary blast was too large to be handled by the primary crushers. Secondary blasting, because of manpower shortage, was largely by mud capping or dobie method. Later, a gelatin was developed which could be spread on the rock with a paddle. This proved more effective than stick dynamite. 3 1/2 cubic yard electric shovels loaded the rock into diesel-powered trucks. These trucks averaged 13 tons per load. The trucks dumped the rock into 2 42-inch gyratory-type primary crushers, which broke it down into 10-inch size or smaller. Limited space made it necessary to locate the aggregate plant on the opposite side of the river. The crushed rock was moved across the river by belt conveyors to a primary storage pile, from which it traveled to the secondary crushers and the rod mills, where some of it was reduced to sand. Excessive fines were removed by a hydro separator, and a large percentage of the water was removed in the classifier. The rock was screened into 4 different sizes. First, the 6-inch size was taken off. Then the material went to the next screen where the 3-inch size rock was screened off, and finally, the 1 1/2 and 3/4 inch sizes. The aggregate plant was geared to produce 500 tons per shift hour for the primary crushers and 750 tons per shift hour for the finished aggregate plant. A belt conveyor in a reclaiming tunnel under the storage piles carried away the rock or sand as it was released through vents in the roof of the tunnel. A final rinse was given the crushed rock to remove sand and fine silty material before going to the mixer plant. The conveyor carries the rock and sand across the river again and around the point of the mountain to the top of the concrete mixing plant. Cement was received by rail in bulk and blown by compressed air through 6-inch pipes to silos located adjacent to the mixing plant. Cement, aggregates, and water were carefully weighed and loaded by gravity into the mixers. 5 4-cubic yard mixers were used, and the mixing cycle was 2 1/2 minutes. The mixers dumped into a wet batch hopper, from which the concrete was taken out onto a belt conveyor as required for placement. Two steel trestles were needed to get the concrete to the foundation. One at the base of the dam and immediately back of the powerhouse. The other, the main trestle, spanning the riverbed. 5,875 tons of structural steel were used in the 3 trestles. The first stage of the main trestle stood over 200 feet high above the riverbed. Concrete was delivered by conveyor into cylindrical hoppers at the end of the trestle, from which it was loaded into 4 cubic yard buckets, placed on a flat car, and hauled by diesel locomotives out onto the trestle within reach of the cranes, where the buckets were picked up and lowered into the forms. The loaded bucket weighed 11 tons. 2 hammerhead cranes with 3 100-foot horizontal booms and 2 whirly cranes placed the concrete from the main trestle. The concrete buckets were of special design and operated by compressed air. Dumping of each 4 cubic yard load was reduced to a matter of seconds. It was immediately compacted into a very dense consistency by electric vibrators. The concrete was placed in 5-foot lifts in blocks 50 feet wide with maximum length 103 feet. In the up and downstream direction, the highest section of the dam was divided into 4 blocks. The diversion tunnels were so designed that after the diversion period, the lower portion could be used to carry water from the spillway. They were lined with 18 inches or more of concrete. A steel form was used to place this lining. The penstocks conduct the water from the reservoir above to the turbines in the powerhouse below. They were fabricated on the job in 20-foot sections and placed by whirly cranes. The inside diameter was 14 feet. The sections were welded together in place and reinforcing steel placed around the pipe in the concrete to withstand the water pressure when the reservoir was filled. The concrete was cooled by miles of embedded thin-walled tubing through which cold water was circulated. Before placing concrete in the block, the old concrete was cleaned by an air and water jet. Then a layer of cement grout was brushed into the surfaces to assure a bond when the regular concrete mix was placed upon it. Concrete placement started in February 1943. From then on, the structure rose swiftly. Concrete was placed on a 24-hour basis, 6 days per week. Every bucket emptied 4 cubic yards of concrete into the forms. Up to 475 cubic yards were placed in a single hour, and over 10,000 cubic yards were placed during a 24-hour period. During 1 month, 240,000, almost 250,000 cubic yards of concrete were lowered into position. The diversion tunnels took the full flow of the river and no difficulty was experienced from seepage in the riverbed area. When the end of the first stage was reached in November 1943, concreting operations totaled more than 1,200,000 yards. The carpenter shops, warehouses, and construction offices were located along the river immediately below the dam. Due to the rugged topography, this level area and all similar areas were graded by the construction forces. Dismantling the first stage trestle in large sections and reassembling it to a point 395 feet above the riverbed took only 2 months. This operation involved the erection of approximately 4,000 tons of steel. Whereas it took several weeks to erect a hammerhead crane originally, Only a few days were needed to reassemble one on the high-level deck. All of the cranes were in operation again at the upper level by late January 1944, and concreting proceeded at a rapid pace. Panel forms on the dam were reused as many as 70 or 80 times. The concrete was placed in steps, each layer being about 18 inches in thickness and thoroughly knit together with mechanical vibrators. Bucket by bucket, a total of 2,800,000 cubic yards of concrete were lowered into place to form a gravity-type structure 480 feet high, 376 feet thick at the base, and 2,365 feet long, including the spillway section. Concrete placement was completed in the dam in early November 1944, being only 20 months from the beginning. Copper seals or water stops in 5-foot lengths were placed on each contraction joint a few feet from the upstream face of the dam to prevent seepage between the blocks as they cooled and contracted. More than 300 instruments were embedded at various points in the dam to measure stress, strain, deflection, uplift, joint opening, and temperature. The data reported by these instruments permitted a careful study of the behavior of the structure under load and are valuable for future design purposes. Many thousands of feet of lumber were salvaged from the reservoir clearing operations, which would have otherwise been lost when the reservoir filled. This proved to be a measure of economy, as lumber was scarce during the war years. Much of this rough lumber was put to good use in the concrete forms. Forms of different types were built at the carpenter shop and taken to their point of use. They could be built in the shop area in panel form much more quickly than they could be built in place. This form is for the spillway outlet structure. It was built in an inverted position, then cut into sections for transportation to point of use. Construction of the powerhouse, located at the downstream toe of the dam, was carried forward so that it could be made ready at about the time the dam was completed. Due to wartime shortage of structural steel, the superstructure, unlike most TVA powerhouses, was constructed of reinforced concrete. Rigid control of the quality of the concrete placed was exercised at all times by the construction engineering department through its laboratory staff. Concrete, as it was placed in the dam, had a very low slump, from 1 to 2 inches. In the main mass of the dam, it had a cement content of only 0.8 to 0.85 barrels per cubic yard. However, the strength in 1 year averaged over 4,000 pounds per square inch. By mid-July 1944, about 2.5 million cubic yards of concrete had been placed. The lower portion of the structure had now reached a stable temperature as a result of cooling operations, and grouting of the contraction joints was started as a final step in the construction of a monolithic structure. The banks of the tail race channel were protected by rock riprap. A rock grapple handled the larger pieces. Rock weighing as much as 8 to 12 tons was needed to withstand the erosion of the spillway discharge. The diversion tunnel was closed in November 1944, permitting placement of the forms for concreting the spillway outlet buckets. Vacuum mats were applied to the surface of the forms, making it possible to remove much of the water near the surface. This resulted in a dense, hard concrete capable of withstanding high discharge velocities. 4 tainter gates, 35 feet high by 35 feet wide, control the flow into the spillway. The gates arrived in small sections and were erected in place. They are hinged on heavy trunnion anchors embedded in the concrete and are operated by hoisting machinery on the roadway deck level. Lining of the shaft leading to the horizontal section of the tunnel and building of the upper portion of the spillway barrel was a very tedious and difficult operation. A fill around the spillway barrels, together with a cut in the adjacent slope, serve as a parking area for visitors. The tunnels were tested in early June 1945 by releasing a small amount of water from the spillway. As the flow increased in the tunnels, the stream jumped clear of the buckets. This discharge was about 19,000 cubic feet per second, which is 10% of the total capacity of the tunnels. The flow of water traveling at such a high velocity was turned up into the air and broken into spray by these buckets or energy dissipators, just as the model test conducted by TVA's hydraulic laboratory had indicated. Rising in the air to a height of over 100 feet, this spray fell some distance downstream into the center of the riverbed, with the tremendous energy of the discharged water dissipated. Water is admitted through the intake structure into the penstocks, through which it is conducted to the turbines. This 34-inch diameter shaft is symbolic of the smooth transition of energy from the turbulent water below to the humming generators above, producing electric energy and providing power for electrifying farms, modern homes, and better living. Thus, Fontana Dam was constructed and now operates as one unit of the TVA water control system. With its contribution to navigation, flood control, and the generation of electric power, it is a giant tool with which the people can further develop the resources of the region.